Hi, in this video we're going back to the idea of derivatives and optimization. It's the second video, that's why there's a 2. But the 2 is also there because we're going to look at the context of functions of 2 variables. And I think actually once you understand what's happening here, you will be able to carry it over even to functions of higher dimensions of more variables than 2. But in the case of 2 variables, you have these nice illustrations because the graph can be plotted like this, where for each point with an x and a y coordinate, here a point, the function value is plotted as the z coordinate, and so you have a unique point for each value of x and y, and together they form this sort of not so well drawn shape, two-dimensional shape, and that's called the graph. And if you look at this, you might wonder, might there be, as for functions of 1 variables, might there be some stationary points, some extreme values, maybe maximum, maybe minimum, and how do we compute them? And actually, the idea of using the derivative carries over to this situation, but with some care. So this is our problem. We have some example here, a function, and we wonder for which values might maximum or minimum values be attained. And how do we compute this? Well, the idea is this. The derivative is not unique in this situation. Actually, you could take derivatives in any direction, but we are going to focus on derivatives in either the x direction or the y direction. And they are called partial derivatives. Why partial? Because you're going to consider the variable to which you do not take a derivative as a constant. So if I look at dx partial derivative, is a derivative with respect to x, and then is a derivative with respect to x, treating y as a constant. And this has a very nice geometric meaning, because if I treat y as a constant, that basically means that I'm in the vertical plane here, going through the value for which y is constant. So imagine a vertical plane here, then there will be an intersection of this plane with the graph, and it might look something like this. Right? So that's a one-dimensional curve. And now the partial derivative is simply the slope of this curve. So as y increases, how does the value of z increases? That type of slope in this intersection plane. So that's a very nice interpretation. And of course, you also have partial derivatives to y. And that will be exactly the same story, only with respect to y, and then you have x as a constant. Okay, so actually computing derivatives like this is pretty straightforward. Let's do this as an example. So the partial derivative of f with respect to x equals 3x squared plus 6y squared. You see, we just treat y as a constant, and therefore this term vanishes if we take a derivative with respect to x, and this one is minus 12. Sometimes you also see the notation like this, with f with a subscript x under it. So that's also compute the partial derivative with respect to y. So it's this, and now this term vanishes, and we have 12xy, and here we have minus 6y squared, and this term vanishes. All right, so pretty straightforward. And here, of course, the meaning is that you have the the vertical plane where x is constant, you have the restriction of the function like that, and then it's the slope of this curve. And that gives us some hint of how to use these partial derivatives for computing stationary points of the function, because they are stationary, exactly, stationary points in case both these partial derivatives are 0. So when f of x in xy equals 0 and f of y in xy equals 0. So again, like with functions of one variable, it's not a guarantee. These are just stationary points. You have to do a little bit of further investigation to see whether actually maximum, minimum, or there's another option here which is called saddle point, but we won't get into that in this video. For the rest of this video, we're just going to compute the stationary points. So here comes a bit of algebra. We get these two equations related to what's written there. So you get 3x squared plus 6y squared minus 12 equals 0. And you get 12 times xy minus 6y squared equals 0. So actually two equations with two unknowns, and well, if these are really complicated, you might not be able to solve them, but of course for this video I chose an example where we can solve it. We're going to start with equation number 2, and we're going to write it like this. It's 2x minus y equals 0, so it decomposes nicely. And then you get 6y equals 0, or 2x minus y equals 0, which means y equals 0, or 2x equals y. Now, these are two cases which we consider separately for the rest. So if y equals 0, what we get with the first equation, which is here, we get 3x squared minus 12 equals 0, which means x squared equals 4. Oh, isn't that nice? That means x is plus or minus 2. And we find 2 points, which is 2, 0 and a minus 2, 0. And then the other case was that 2x equals y. In that case, I get, filling it in here in the first equation, I get 3x squared plus 6 times y squared. Well, y squared is 2x squared, so it's 4x squared. So 4x squared minus 12 equals 0. So that's about 27x squared equals 12. Okay, this is all a bit tedious, but let's not give up. 12 divided by 27. So x is equal to the square root of this, plus or minus the square root of 12 divided by 27. Now, actually, this could be simplified a little bit, right? We could divide both by 3. So we get 4 divided by 9. Which is a nice square root. It's 2/3, so it's plus or minus 2/3. And that gives us another 2 points. So 2 over 3, comma, what was y? Oh, y was twice, no, not exactly. Y is half of, no, y is twice of x, twice x. So that's 4 over 3. And with the minus, minus 2 over 3, comma, minus 4 over 3. And they're both stationary points, like this. Okay, so what have we learned? We've learned that in the case of functions of two variables, there are actually two partial derivatives, although you could actually take derivatives in any direction, but that's not in this video. Two partial derivatives, and they have nice geometric meanings. because they are the slope of the curve that you get when you intersect with these vertical planes. Then we can use this to find stationary points, because that's exactly when the slope of these two curves equals 0, and then actually the tangent plane will be horizontal. And well, we can use this then to compute what the stationary points is, and that's generally not very straightforward, because you need to have equations that you can solve. And you solve them usually consecutively, combining them in a clever way. This is what you get. All right, so I hope this helps you, and success.